This right here is the brunt of what I've been working on and the culmination of everything I've been working on since HRM as far as pertaining to the bed leveling. I'll start with this right here. I went on SolidWorks forum and read this thread about threading, no pun intended. And the suggestion here was to use 2D opposed to 3D for simulations. And I read further and further about this, ultimately getting to the conclusion that through all these suggestions, the takeaway I had was it's best to use the formulas that have been used prior to all these softwares being available for these kind of simulations. From what I read, long story short, it said that the formulas have stood the test of time. The simulations are somewhat tricky when it comes to threading because of things like surface area engagement, etc., and the fact that this first thread will bend in reality when there's a force on it, and the sequential threads will get less and less force applied to them as it goes down the chain. So to start, what I did was I found this formula right here, and what we want to know is the torque, and I had to work backwards with the axial bolt force. I was able to find this value from this chart right here. This is from Stanley's website, and for a quarter 20 halo coil, this is the chart that you can use. The material that we're using, the halo coil, or I should say the material we're inserting the halo coil into is 6061 T6 aluminum. And you follow this line until it intersects the the length of the helical that you're using. In this case, I chose a 3/8 of an inch length, which is 1.5 times the diameter. And where that length helical intersects the 6061, you go across here and we have 6,000, well, roughly 6,750 pounds of tensile strength, which at first when I read this, I thought that this must be a mistake. I must not be reading this correctly. Then I looked at other values, for example, a 440 helicoil, and for the same material and even less length, 1.5 times the diameter of a 440, the value was 750 pounds, which seemed somewhat more reasonable to me. So I decided to use MATLAB and plug in these values to that formula I just showed and came up with this script here where I do all the conversions to metric, etc. So I'm going to rerun this. When I run this code here, I enter in all the values up here so that this can be used in the future if anybody else needs it. And we get the torque pound per inch 325. Given the parameters of what we're working with. I also found an online calculator and double checked this, and I got the exact same value. The major diameter is 0.25 inches. The friction coefficient, we're dealing with stainless steel. I chose to just stick with the 0.2. And the axial bolt's clamping force is 6,500, 325 torque. That actually seems reasonable to me. What I mean by that is when we tested the ER11 collet, we hit 200 inch-pounds of torque. And that seemed somewhat substantial to me. And I do feel like if I added another 50% more force than what I was tightening that collet nut down with, I could probably strip out a set screw. And this put my mind at ease as far as this value of 6,500 pounds. Once it gets converted to torque, I'm dealing with numbers and values and forces that I'm used to dealing with in everyday life for a long period of time, and it's something that I can relate to and gauge whether or not this seems like a realistic number, and it does. What this script also does, it divides out that torque by 4 so you know how much you have to torque each one of the bolts, and I'll explain in a second why it's divided by 4. I just want to also mention that I also convert everything to Newton millimeters here as well in this script. So we have 225, and that ends up being the 81.25 inch-pounds max per bolt. What I mean by that is here, every set screw is going to be surrounded by 4 bolts. So we have to divide out that 325 by 4. Now, the set screw is also going to be going down beneath this here and pressing against this steel barrier that I put right here to lift this plate up slightly. When that happens, the set screw is no longer going to be engaged, and the full 3/8 helical that is going to be inserted in this 1/2 inch thick plate. It will be slightly less. So I decided to cut the value of 80 down to 50 inch-pounds per bolt to be on the safe side because we don't want this to rip out. So let's say we max out the torque at 50. Okay, that's 50 times 4. We have 50 inch-pounds on all 4 of these. That's 200 inch-pounds torque, which is significant. But we also have that being applied at 1, 2, 3, 4, and then under here, 5 different places. 200 times 5 is 1,000 inch-pounds torque, making this plate hold on to the rest of the machine. It's going to secure this plate to the frame through these parts, through here, into these screws, which go to here, and then that is attached to the frame. So that is how we're going to secure this plate to here through 1,000 inch-pounds of force applied and distributed through all these points, these 5 points that I just mentioned. So in my mind, that is significant, and I see the 20 pounds of force that the milling is going to be doing, and I got that value from last year's MQP report. I see that as plenty of torque, also a reasonable value to not rip out the set screw. So I think we should be good with these values. I'm looking forward to doing the actual testing on the plate that's currently in the machine that we have from last year right now. And cross my fingers, hope all these calculations end up working out for us.